Okay, great. Hi, I'm Brian Homerding. I'm going to provide a quick introduction to Kokkos and a little bit of a quick start in case you're interested in using it. So to start with, kind of what is Kokkos if you're not familiar? It's a C++ programming model for performance portability. So it's used kind of across a wide range of institutions. The main difference here is that there's no direct compiler support like there is in OpenMP and SYCL. Instead, it's implemented at a higher level of abstraction as a template library on top of these other programming models such as CUDA, OpenMP, and SYCL. So on Aurora, the kind of recommended backend is SYCL. So that's going to be what I'm using in the examples later. So one thing to consider there is that you get the benefit where you get to kind of use whatever the best vendor supported backend is going to be. The downside is you are adding an extra layer of abstraction. So Kokkos itself is aiming to be descriptive and not prescriptive, and it tries to align with the C++ standard as much as possible. But beyond the programming model, it's kind of also providing solutions for the modern needs of science and engineering codes. This includes math libraries and various tools. So there's support based on these, which I'll kind of touch base on a little bit next slide. It's open sourced. It's a Linux Foundation project. And like I said, it has a lot of users across many institutions, especially in the DOE. So this is a broad picture of the Kokkos ecosystem. So if you look dead center, there's the Kokkos core. This is what I'm going to be showing about. This is the programming model. This covers the parallel execution and the parallel data structures. But just to touch that beyond that, there's a lot more other things kind of going on. So there's Kokkos kernels. This covers all your like linear algebra kernels, graph kernels, as well as Kokkos tools to have better support for debugging, profiling, and tuning. There's a lot of good support online that I'll end with a bunch of pointers to. And then there's a few other projects that are kind of floating around here on the outsides. So in the Kokkos core, there's kind of two high-level abstractions that are very important to the whole programming model as the data structures and the parallel execution. So in the data structures, you're going to be specifying memory spaces or where, memory layouts, and then also memory traits, basically how we're accessing. And then on the other side, you have the parallel execution. So this is, you can specify execution spaces, whether you're on the CPU, GPU, specifying where. Also, you can create execution spaces for different GPUs if you need to, if you want to use like multiple GPUs inside a single process. Then you have execution patterns, which I'll touch a little bit more on, but these are kind of the common parallel patterns that you're going to be using, and there's various ones that are supported, and I'll show an example a little later. Then you have the execution policy, basically saying, okay, how do I actually execute this? So to give you an idea what this looks like, I'm going to go through a quick example here. So the quick example being a conjugate gradient solver. So this is a simple iterative linear solver. It's used in the MiniFE proxy application. It has three math operations. We're only going to look at the first one, just in the need of time. So we're going to look at this vector addition. And then before going on to that, we'll touch on the data management. I'll go more into detail on this in a later slide. So before we go into like a parallel kernel where you have like a parallel 4, you're going to be using these views. It's a very important object in Kokkos. So here it's, if you're kind of familiar with CUDA programming, you're creating a host array with some input and the extent of it. Then you're going to create another array. This will be on the memory space on the GPU with the same extent. Then you can perform a deep copy. Kind of like allocating memory on the CPU, filling it, GPU, copy it over, and then pull it back when you need it. So for that vector addition, this is a simple data parallel loop. It's a Kokkos parallel 4. This is easy to express in most programming models. This is what's been used in the examples for the other ones also. It's bandwidth bound. So on the top here, you have the serial implementation, and on the bottom is the Kokkos implementation. Now, to get an idea what's different here, a few things that are not super big. One, instead of kind of double pointers to arrays, we're having views to double pointers of arrays. That's just using the Kokkos data structures. Then the for loop is going to be a parallel for, a Kokkos parallel for, which does look quite a bit different, and I'll go into more detail on that. But then when we look at the loop body, it's the same exact loop body, only now we're using parentheses to access the views instead of brackets. So looking at this for line, first off, you have a parallel for, so this is specifying the parallel pattern. So this one's a parallel for, it's kind of a do-all loop, fork join parallelism. There's also parallel reduce and parallel scan as some other parallel patterns. Next up is a string label. So this obviously is nowhere to be seen in serial implementation. This is if you're familiar with C++ and you've used any kind of template libraries, things get very nested very quickly. So this is to help better support profiling and debugging tools so that it can have a string to help tie a specific kernel back to your tool, as opposed to having a big giant templated name. Then we have the execution policy saying in iterations. And then you have your iteration handle. This is what's getting passed into this Lambda. And I'll go a little bit more into Lambda just to give you a quick overview in case you're not familiar with that C++ kind of construct, because it's very important for these higher level abstraction libraries like Kokkos or Raj. And finally, the loop body being about the same, just using parentheses. So for Kokkos parallelism, the simple usage is very similar to OpenMP, but the advanced features are also pretty straightforward to use. There's 3 common data parallel patterns. So I mentioned data parallel for, and parallel reduce and parallel scan. These are kind of the ones that are going to cover most of your use cases, but you also have support for building like task tags and things like that. Each parallel computation is characterized by that pattern, but also the policy and the loop body, basically saying how to execute it and what are you executing. So the bodies are provided by the user as computational bodies. These are provided as either functors or lambdas, which handle a single work item. Just think of it as handling a single iteration. So the top is similar to the last example, a little trimmed down. Basically, so the lambda part is you start with this bracket with an equal sign in it. This is basically saying how to capture values. So the equal sign says capture by value instead of a reference. It's important because, especially with the SQL backend, everything needs to be captured by value. Then you're going to be having your basically the argument parameters that are going to get passed into your function. So lambda is just kind of creating an unnamed function. And then the loop body that's going into it. Now, this is a functor for the same exact lambda, but the difference being here, instead of kind of specifying it in line, you can specify this wherever you want in your code, just as a struct. And then we get passed in as the third argument to the parallel for. So here you're just overloading that function operator. Oh, sorry, to do the execution of the loop. So this is the exact same thing in the back end. Whether you write it this way or this way, it's kind of up to preference, or whether you're going to be reusing that functor across different places or not might influence which choice you want to make. But essentially, the compiler is taking a lambda and turning it into a functor for you. Now for Kokkos memory management, just to cover a little bit more on that, I went through super briefly earlier, but so data is stored in views, which are kind of pointers to multidimensional arrays residing in different memory spaces. The views abstract away platform-dependent allocation, deallocation, and access. So you're never having to do a CUDA-alloc. You're just using Kokkos views. The heterogeneous nodes, such as the ones on Polaris and Aurora, there's different memory spaces from the GPU and the CPU. And the recommended thing here is mirroring for performant accesses across views in host and device memory. So I'll kind of cover what mirroring is, just to give you a basic idea. If you're familiar with any GPU programming, this is going to look pretty familiar. So this is just the Kokkos version of that. So first, we're going to create a view in device memory. So we're specifying this type as a view type. It's a Kokkos view of a double pointer, and has a memory space. So this will be the GPU space. We'll initialize it. And then we're going to create a mirror view. So this is this Kokkos create mirror. So what this does is create a view on the host of that view. And create mirror will always kind of allocate some data for you. There's also a create mirror view, which will only allocate if it's not accessible on the host. So now we basically have a, a multi-dimensional array on the host, a multi-dimensional array on the device, and we're going to populate the one on the host from our input file or data generator, however you want to go. Then we're going to copy it to the device. So we perform a deep copy, should be an underscore here, sorry about that. From the host to the device, then we're going to use it into our parallel for. Then you would perform a deep copy back if needed. So for a quick start, one of the things I mentioned with all the kind of support, there's these tutorials. So if you want to follow along with this, you can git clone the Kokkos tutorials. And then on Aurora, there's already kind of a built Kokkos, so you can just module load Kokkos in CMake. So when you module load Kokkos, if you check your environment for Kokkos, you'll see that it's setting this Kokkos root variable, which is going to be used if you properly kind of set up your project to use Kokkos with CMake. Then when you want, you can go into it. Obviously, there's a bunch of PowerPoint presentations and various other things inside these tutorials, but if you go into exercises, there's a bunch of different ones for you to work on. Each one of them is going to have this begin and solution inside. So the beginning is going to be kind of a program with a bunch of stuff missing that has comments instead saying what you need to implement. And then the solution is just kind of something that you can build and run directly and what you're aiming to do. When you finish kind of constructing the solution out of your beginnings point, you can compile it. This is kind of the easiest way. So this is just using CMake, which we loaded earlier, setting the build directory to build SYCL. And then the main thing here is you need to find this Kokkos enable SYCL on. This is just saying build it with support for the SYCL backend. Then you can compile it. So as mentioned, this is running SYCL in the back end. So if you're going to run a profiling tool or anything on it, it's going to work perfectly. It's just going to look like it's running SYCL code. There is some more support. This is just building a kind of run on the CPU and then offload to the GPU. But there are some examples for like MPI, and there's an example on the getting started page of how to build with MPI for Kokkos, and as well as how to do the AOT compilation in the getting started, which I left a pointer to here. So I mentioned a few of these, but just so they're all in one place. You have the Kokkos tutorials if you want some kind of simple getting started place to try to learn. There's also these lectures available with pointers here through the Kokkos documentation. There's the documentation itself, which covers everything, and the GitHub where you can open issues or look at previous issues. As far as running on Aurora, there is a page like all the programming models for running on Aurora. I mentioned this also helps you cover how to compile with MPI and how to specify so that you want to do ahead of time compilation. Then I just added a link for the running jobs on Aurora. This is for everybody. Finally, if you need help, there's the ALCF help. There's the Slack for the workshop, of course. And then there's a Kokkos Slack that you could join also if you end up using Kokkos. And with that, that would be the end of the Kokkos introduction.